Hello everyone, my name is Cole Quake, and today I'll be presenting my research on daytime radiative cooling coatings in hot, humid climates, with a specific focus on Houston. This project was completed for MECE 6333, Conduction and Radiation, at the University of Houston during the fall semester of 2025. The goal of this work was to understand whether radiative cooling, which is well known to work in dry climates, can still be effective in the Gulf Coast where humidity is extremely high. Radiative cooling is a passive cooling method that rejects heat to outer space by emitting infrared radiation through the 8 to 13 micron atmosphere window. It has the potential to reduce building cooling loads without using any electricity. However, Houston's climate introduces major challenges: high humidity, frequent cloud cover, and strong diurnal swings. All of these affect how much radiative heat can actually escape to the sky. The atmospheric window, between 8 and 13 microns, is the key mechanism that makes radiative cooling possible. The atmosphere is relatively transparent in this band, but in humid climates, water vapor absorbs strongly within this same region. That narrows the window and raises the effective sky temperature. As a result, the sky becomes a weaker heat sink, meaning radiative cooling potential drops significantly. This project had 4 major objectives. First, we needed to evaluate the feasibility of radiative cooling in Houston. The second was to quantify how humidity affects cooling potential. Third was to identify the optical properties a material would need to be effective here. And finally, for fourth, we were to model how cooling varies throughout the day. To do this, I used a radiative convective energy balance model. The model includes a gray sky emissivity formulation that captures how humidity and cloud fraction affect sky temperature. It also includes wind-based convection because Houston's afternoon sea breeze plays an important role. Then, using parametric sweeps, I evaluated performance across different combinations of solar absorptivity and thermal emissivity. This figure shows the predicted cooling potential, the difference between ambient temperature and surface temperature, across a range of material properties. The key trend is that cooling quickly collapses as solar absorptivity increases. To get subambient cooling in Houston, a material needs to be extremely reflective in the solar band and highly emissive in the infrared. When this figure was generated, a few of the numerals were generated beyond the graph, but using interpolation, you can see that the first numeral on the left in the most green line is 2.4, followed by 1.6. These next two numerals are 0.8 and 0.0, then followed by the numerals that can be seen, which is negative 0.8, negative 1.6, and so on. The design window here, outlined in white, represents the performance of state-of-the-art radiative cooling coatings reported in literature. What's interesting is that the feasible cooling region overlaps almost exactly with the radiative cooling coatings. This means that technology can work in Houston, but only if we use top-tier ultra-reflective coatings with solar absorptivity below about 0.06. This plot shows performance across 4 time points during the day. In the morning, humidity is extremely high, often above 90%, so cooling potential is very limited. But as the day progresses, humidity drops and wind speed increases. The strongest cooling happens in the afternoon, where conditions are most favorable, even though the solar load is high. And you can see here that the hours that I used for the 4 points is 9 a.m., 12 p.m., 3 p.m., and 6 p.m. This lower line is the delta T, which we mimicked back in figure Y. This figure highlights how dominant humidity is. As relative humidity increases from about 40 to 80%, cooling potential drops by roughly 60%. This explains why radiative cooling works well in dry climates like Arizona, but your performance in Houston is much more constrained. Here, we can see how sky emissivity depends on water vapor content. Higher vapor pressure directly increases sky emissivity, which raises the effective sky temperature. This is critical because radiative cooling works by emitting heat to a cold sky. But when humidity increases, that cold sink warms up, reducing the net radiative loss. This bar chart illustrates the competing heat fluxes acting on a radiative cooling surface. On one side is absorbed solar radiation. On the other side are infrared emission and convection. Radiative cooling is only achieved when the infrared emission exceeds the combined solar absorption and convective gains. This balance becomes much harder in humid climates unless solar absorption is extremely low. To summarize humidity effects, it's the single strongest environmental constraint. High humidity narrows the atmospheric window and raises sky temperature. Cooling often becomes impossible in the early morning. So any radiative cooling strategy in the Gulf Coast must be evaluated with humidity as the central factor. In this figure, going back to what was previously mentioned, you can see that this actually functions linearly. And yes, as humidity increases, our normalized cooling potential does decrease linearly. So that relationship is important. Convection plays an interesting supporting role. Houston's afternoon breeze boosts the convective heat transfer coefficient, which helps remove any absorbed solar heat. Convection can't overcome humidity, but it can enhance cooling during the best hours of the day. These results lead to very clear material design criteria. Solar absorptivity must be below about 0.06. This is the most important variable. Thermal emissivity should be above 0.90. Even small deviations from these ranges dramatically reduce performance in humid conditions, which we can see back in figure Y. This vertical line here is our solar absorptivity at 0.06. The horizontal line is our thermal emissivity, epsilon, at 0.90. Now you can see that if you extend this vertical line for the solar absorptivity, that the range remains relatively similar. However, we get optimized performance above a thermal emissivity of 0.9. Overall, radiative cooling is feasible in Houston, but the performance is modest, typically 1 to 3 degrees Celsius below ambient during the best hours. While this is lower than what's achieved in dry climates, it is still meaningful for reducing roof temperatures and lowering peak cooling loads. Future work involves incorporating full spectral atmospheric modeling to better capture humidity effects, running year-long simulations using actual NOAA data, and performing rooftop experiments locally. Hybrid strategies, like combining radiative cooling with evaporation or phase change materials, also show promise for improving performance. Thank you, and you have a wonderful rest of your day.